Good morning, everybody. So we stay with synchrotron light and electrons, electronic properties of materials, and we go for synchrotron photoemission spectroscopy, core levels, valence levels, and environment. The basic contents of what I want to cover today is photoelectrons or photoemission spectroscopy. It's two different terms for the same thing. For those of you who are not very familiar with it, just how it fundamentally works. And since you can buy off-the-shelf photoemission spectroscopy setups for the lab with light sources for the lab, I will then focus on examples why it may be useful to go to the synchrotron radiation facility instead of just staying in your lab. And there are a number of good reasons. For instance, if you want to change the depth information of the sample that you're investigating. If you have a complicated sample, you may play with the cross sections for the photoelectron yield. If we want to study how a certain element contributes to the valence band, we can go for resonant photoemission. And if you're interested in details of the band structure of a crystalline material, so basically the energy versus momentum relation, sometimes the brilliant zone of a sample with a very large brilliant zone cannot be reached easily in the lab in angle resolved photoemission, so you might want to go to the synchrotron instead. And there are also information possibilities beyond just the electronic properties based on photoelectrons. One is the bonding distance of adsorbates at a surface, and of course also microscopy, which can be superior at the synchrotron. And finally, a note on environmental photoemission that can be done, of course, in the lab, but also with various forms at the synchrotron. Very basics of photoelectron spectroscopy. We have our sample typically residing in ultra-high vacuum to keep the surface very clean. And then we irradiate it with monochromatic light of energy h nu. Photoelectrons are kicked out and their kinetic energy is measured then in an electron spectrometer. The energy levels are schematically shown here. So we have our sample, we have the Fermi level of our sample, we have the valence electronic levels or the valence band, deeper in energy with a higher binding energy, we have the core levels. Our sample has a certain work function, that's the energy difference between the Fermi level and the vacuum level, which is the electrostatic potential zero just above the surface. And if we come in with a photon energy h nu, for instance, this magnitude, we can then get a core level ejected from our sample, and this electron from the core level has to overcome the binding energy, which is typically referred to the Fermi level in photoelectron spectroscopy. That electron has to overcome the work function of the sample to leave the surface, and then in vacuum it will have a certain kinetic energy E prime. Electrons from the sample have to move to the spectrometer. Spectrometer and sample are electrically connected, meaning the Fermi levels are aligned, and very often the work function of your spectrometer will be different than the work function of your sample. So in the case shown here, it will be that the electron emitted from the sample will see a rise in the electrostatic potential, and it will arrive in the spectrometer with a smaller kinetic energy than it has left the sample, which is no problem because we can use the energy conservation relation shown here, that we know that the energy of the incoming photon will always be divided into the work function of the spectrometer, the binding energy of the electron in the sample with respect to the Fermi level, and the kinetic energy that we measure in the spectrometer. And the only relevant information that we want to have is this binding energy with respect to the Fermi level. So what was the binding energy of the electron in the solid before it has left? Terminology, when you do this in the UV region, so the light is in the UV regime, then we speak of ultraviolet photoelectron spectroscopy, and if the photons are in the X-ray regime, we speak of X-ray photoelectron spectroscopy, XPS. So beyond this binding energy of a core level, what else can we get from a total spectrum that we take if from a sample when we just measure the intensity of photoelectrons emitted versus their binding energy. Here we show, for instance, in red, to start with, what we can learn from the valence electronic levels of the structure. So either it could be the valence band, as said before. If you have a molecular material, it could also be emission from the highest occupied molecular orbital, or HOMO -1, 2, 3, and so on. If we go ahead and also measure the secondary electron cutoff from our sample, essentially what is the energy of electrons just leaving the sample with almost zero kinetic energy with respect to our spectrometer, we can then also determine the work function of our sample experimentally directly. And if we know then the onset of ionization from the valence levels, we can get with the work function also the ionization energy of our sample. As a side note, you can do the timed reverse experiment to photoemission, meaning you can come in with an electron and measure a photon coming out. This would be inverse photoelectron spectroscopy, which of course you don't do at a synchrotron because you need slow electrons coming to a sample. But with that method, you can also infer then information about the empty states of your sample. So the LUMO, if you have a molecular material, or the conduction band structure if you have a conventional material, and therefore also get the electron affinity. This is something separate. If we have X-rays exciting our sample, we can also access the core levels, and that of course has a rich information depth, meaning you get the stoichiometry of your sample, of course with a certain caveat, and you get the chemical environment of individual elements that you have in your sample. The only challenge that is still remaining, particularly with the emerging new materials that are available, which are not always very resistant to high energy photons or the myriad of electrons that you're creating in your sample, we have to adapt the methods UPS, XPS to the special requirements of these novel and potentially radiation sensitive materials, and also take extreme note of the sample handling and the sample history during the experiment. Otherwise, we might run into problems of interpreting the data. Now, what is the basic information we get from core level photoemission spectroscopy? Already in the previous talk, you have heard that the electronic structure of each element is characteristic of the filled electronic orbitals of the atoms, and therefore each atom species, like copper or nickel, will have a different binding energy of the individual core levels. So just by looking at the binding energy of the peaks that you measure, you can identify the element that is there. And also we get for free not only the core level photoemission from such a spectrum, since you also have Auger processes and electrons of the Auger type are emitted, you also get the Auger transitions, which can further help you identify elements in your sample. And for that reason, the historic name of X-ray photoelectron spectroscopy is actually electron spectroscopy for chemical analysis, or ESCHE, which you will find in literature as well. Now, once you have identified an element, you can zoom into one of the core levels that you have recorded and look into more detail whether you have only one type of this particular element present or whether you have different types of that element present in terms of within a material. Here's an example that's about a monolayer of this molecule pentacene, a pure hydrocarbon. And when we look at the carbon 1s core level of a molecular layer on the gold surface, we see only one symmetric peak, meaning we have only one type of carbon in that molecule, and that is quite obvious. What you can do is you can go and replace all the hydrogens at the periphery of the molecule by fluorine atoms to change the electron affinity and ionization energy of the molecule. And when you then look into details of the carbon 1s core level, you see two peaks instead of only one for the pentacene. For the perfluoropentacene, we can see clear two carbon peaks separated by a huge binding energy difference. And that's then the binding energy difference of carbons that are bound to a fluorine and carbons that are not bound to a fluorine. Fluorine has a very electron withdrawing character, so the carbons bound to fluorine appear at a higher binding energy. And this can be done for essentially anything that you have in your sample and look at the stoichiometry and different chemistry of your sample. Now, what can you do in principle in the lab? What we know is that there is a certain electron mean free path of electrons with a certain kinetic energy. Here the electron energy above the Fermi level is given, but by all practically means you can just think of that as the kinetic energy of the electrons leaving your sample. And of course, characteristic of what you have in your sample are only those electrons that have not been inelastically scattered on the way out. So, and this is then the mean free path an electron can fly in a material without being inelastically scattered. And we see that for typically UV sources in the lab, we have a very short mean free path. And for typical X-ray sources in the lab, this path increases to some extent. So for what we have in the lab, typically the information depths from the surface will range from a few angstroms to a few nanometers only. If you look at this mean free path calculation, 95% of the information that you get comes about from a depth 3 times the mean free path lambda. So you will be always very surface sensitive with this method. But to some extent, at least, you can change and select the surface sensitivity of your measurement by changing the photon energy. And this is where synchrotron radiation comes into play big time. You are not limited to the typical energies you find in laboratory light sources. You can go to much higher excitation energies and therefore also to much higher kinetic energies of the electrons that you are exciting from your core levels, and therefore you can look deeper into the sample. And this is an example from a structure that is copper, indium, gallium selenide, so a solar cell absorber that is covered with a zinc, oxygen, and sulfur containing buffer layer that is about 15 nanometers thick. So in a standard laboratory experiment with 1500 eV excitation energy, or here at the synchrotron 3000 eV in the bottommost spectrum, there is no way we get any information from the CIGS layer that is buried beyond the buffer. But as we increase the photon energy, in this case up to 9000 eV, we see gradually an increase of a signal that's coming up here, showing in the inset. That's the selenium 2p core level. So we start seeing information from a CIGS absorber below the 15 nanometer thick buffer layer. And therefore, when we go for these higher energies typically available at synchrotrons, we can look deeper into a sample and we can actually make some kind of depth profiling of an entire device as long as the device is around 30 nanometers thick. This is the practical thickness that we can go for with this high energy photoemission or HAXPES very often in at synchrotron light sources, as it is called. And also, of course, you can look in details of chemical shifts and look at electronic and stoichiometric properties of interfaces that are buried between below something that is protecting it. So this is one thing you can play with at the synchrotron. The other one is, of course, the photoionization cross-section. And the previous speaker has already pointed out that the total absorption of photons of a given element follows about this behavior that the higher the photon energy, the lower the photon absorption cross-section, but we have sudden jumps at a certain absorption edge. This was discussed with X-ray absorption. So if you now play with the photon energy in a sample that contains many different elements, by changing the photon energy, you can deplete or enhance, so attenuate or enhance the contribution of a certain element to your photoelectron spectra, if you're hunting, for instance, for small amounts only. And the same trends, but in more with a little bit more complication, also holds for molecular materials, that the emission from individual molecular orbital varies significantly with the photon energy. And here's an example of a hydrocarbon molecule again. And we see when we go from 22 to 43 V, there's a substantial change in the relative intensities of the individual molecular orbital levels. And this can then also be used to enhance emission from those that you are particularly interested in. Now, since we are already at information from the valence band, there's another way you can interrogate your sample with respect to the valence levels in even more detail. So this is then resonant photoemission spectroscopy. In the classical photoemission experiment, what you do is, as I said, you come in with a photon of a defined energy h nu, and you directly kick out an electron from the valence band. You measure its kinetic energy, and you know the binding energy of that valence band or molecular level. Now, if you tune your photon energy that is coming in a way that it can also be directly absorbed by one of the core levels that an element has, then a new emission channel opens up that is called Auger relaxation or autoionization. So instead of just directly kicking out an electron from the valence band, you can also have then a core level electron of their sample promoted to an empty state. So that's the X-ray absorption process. This electron can relax back to the core level, and of course here it has to lose energy, and it transfers the energy to an electron from the valence band, which then gets emitted with the same kinetic energy as an electron that is directly promoted from the valence band itself. So as long as you now have this core level absorption possible, you have additional intensity to your spectrum from that particular valence band that is involved in that process. So you get information that is specific for an element, and you can probe to what extent that particular element contributes to which part of the valence band structure. Here's an example from practice. This is a multi-layer of this molecule, PDCDA, not PDA, sorry for the mistake, on a gold surface. Here is the absorption measured at the carbon edge for this particular material. And here are the valence band spectra of the molecular layer recorded at each individual photon energy that is shown here. And we see, as we tune through the absorption details of that particular material, we see huge changes in the emission intensity from individual molecular materials that involve more or less carbon and that have then a particular relation to the absorption details at the core level as well. So we can learn about the contribution of the individual carbon atoms to the individual molecular orbitals. Same also for another material, and here's the interface of two different oxides that are quite interesting in electronics. And when we do just regular photoemission, so off resonance, we get the red spectrum, and we zoom in close to the Fermi level at 0, we see basically nothing. It just shows a flat attenuation of the intensity. When we go and measure on the titanium L edge, so we do photoemission resonance, then we see a strong signal here as the blue curve, and that is the signature then of charge carriers that are trapped in the d orbitals of the titanium ions, and the evidence is that we have mobile interface charge carriers. So only by the enhancement in resonant photoemission it is possible to see these states that exist, which are just not strong enough in emission when we do an off resonance measurement. Next case where synchrotron radiation comes in quite handy is you might have a crystalline material that you want to study, and you want to study the valence band structure, as I said, the dispersion of electrons, their energy versus their momentum. And depending on the size of your the unit cell of your crystal, you will have different sizes of the brilliance zone that you want to study completely. And in angle-resolved photoemission, the momentum of the electrons outside is the same as the electron momentum inside, parallel to the sample surface. And this is then related to the angle that you detect and the kinetic energy of your photon. So if you have to go for very large K values, you have to increase the kinetic energy to reach these large K values. And therefore, just increase the photon energy beyond what is available in the lab, go for a synchrotron. And at a synchrotron, you can go to very high energies. For instance, here, an example of 4000 eV excitation of your sample. And you don't see information only from one brilliant zone, you see information from several brilliant zones, and you can learn more details about the band structure or the extended band structure of your sample. Of course, it is nice to get the in-plane band dispersion of your sample, but sometimes you also want to know what is happening in the surface normal direction, so the vertical direction. In the vertical direction, the momentum of the electron is not conserved, but still it is proportional to the square root of the kinetic energy of your sample. So if you just vary the kinetic energy of the electrons emitted from valence band states, you get the dispersion in the surface normal direction. And you then get, for instance, that is shown here for a perovskite material, for a certain part of the brilliance zone, you get the band dispersion in the surface normal direction. And you need this fine-tuning of the photon energy on the one hand to reach the kinetic energy, to tune the depth of the K vector, and also to record the dependence of the energy relative to the vacuum level of final states, photon energy, to get this inner potential of your sample. Now, this is a method that goes beyond just electronic structure. This gives you structural information. Think you have a crystal with an adsorbate on the surface. If you come in with photons of an energy very close to or at the Bragg condition for diffraction in the surface normal direction, you will have the superposition of your incident X-ray wave and of the diffracted X-ray wave, meaning that you will create a standing wave pattern of nodes and maxima just above your surface. And depending on where your adsorbate is, it can lie then in a node or in a maximum of that standing wave. And if it's in the maximum of a standing wave, the photoelectron yield from a certain element will be enhanced. Otherwise, it will be reduced. And just by looking at how we detune the photon energy from the exact Bragg condition, we are moving then the standing wave maxima in front of your surface up and down slightly by fractions of an angstrom, and we see how then the photoelectron yield of the fraction of how the photoelectron yield of the adsorbate changes with its distance. So just by measuring all these red curves, you can get an idea on the bonding distance of that adsorbate with sub-angstrom precision. Here's an example of a molecule that contains carbon, fluorine, and nitrogen adsorbed on a copper surface. And when you do X-ray standing wave experiment, you can measure the core level intensity of all these when you move through the Bragg condition. And from details of how the intensity change, one can get experimentally the exact bonding distances of the average carbon atoms, but also the nitrogen and the fluorine. And here it was found that there are significant bonding distance differences between the elements, meaning the molecule is bent at the surface. And of course, there's another way you can play with photoelectrons, that is then photoelectron microscopy. Can be done in the lab, but sometimes there's a good reason to go for the synchrotron for that, to change, for instance, the photon energy. Here's an example of a graphene layer that is sandwiched between two boron nitride layers. And then we do photoemission on that with a very small spot at the synchrotron. And the entire thing is put up in a way that you can actually gate the graphene, like in a field effect transistor. And it is possible then to see how the energy levels close to the drag point of graphene can be depleted, or whether you can actually N-type dope your sample depending on the bias that you put on your gate. So this would be the playing around of Brando photoemission microscopy in the electronic sense. And finally, nowadays it is not necessary that you do all these experiments in perfect ultra-high vacuum. You can backfill your chamber with a certain gas that you're pretty much free to select, up to several 10 millibar of that gas, and then do photoemission during the sample surface being exposed to that particular type of gas molecules. So you can see how certain environmental aspects, exposures change the surface stoichiometry of your sample, or particular for catalysis, you can do operando catalysis study with photoemission spectroscopy. To wrap up, there are a couple of reasons that you should go for the synchrotron and not stay at home in the lab. If you want to take care of the depth variation, if you want to investigate more depth of your sample, if you want to play with cross sections for a very complicated sample stoichiometry, to do resonant photoemission, to learn details about which atomic species contributes where to the valence band, extended beryllium zone sample in angle-resolved photoelectron spectroscopy, learn more about very details of the bonding distance of adsorbates, or do microscopy studies, and go for the environmental changes that I have mentioned at the end. Thank you for your attention.